So it's always a bit unclear what you should do for a final lecture since everybody's getting ready to go home again and this is already over. So what is the right topic? And initially I thought that I would talk about these radical formulas from the beginning, since there's a general rule if you start something, a course, yeah, so several lectures, in the end you come back to something from the beginning. So I could show that certain equations cannot be solved by radicals, do solvability. But then I realized that Bas is in the audience, and he would simply say, well, that's 19th century stuff. Who is interested in radicals anymore? And he might say so right at the beginning of my talk, I have to change the topic. So I listened to him a little bit and he said, well, mention Frobenius. So I thought, okay, let's mention Frobenius. So I will try and mention Frobenius and still get back to my first lecture, which was on explicit questions. And if you get home, which you may now very soon, and your grandmother asks you, what did you learn about this Galois theory? Then you say, well, I learned that polynomials have a Galois group. And you say, Granny, you have a field f and a splitting field. You take your polynomial f in fx, you know. You form the splitting field of f over f. Split f, f. And you call it k. And I learned about this Galois group of k over f, which holds all the secrets of this extension. And you ask, what is a Galois group? And you'll say, well, that's a finite group that comes with the polynomial. Oh, finite groups, yeah, when I was young they existed already, they're also in the 19th century, you'll say. So if I give you a polynomial, you can give me the Galois group. You say, maybe, right? So you ask her, which polynomial would you like to know the Galois group of? And you hope that she sort of gives a very easy answer. Well, what about x squared plus 1? Something like this, since you may know about complex numbers, square root of minus 1, I think that should be a complex example. If that's your f, what is then your answer to your grandmother? What's the group that you have to associate to this? You're about to get home, right? And you just replace maybe then your grandmother by your neighbor, who's an engineer. He knows how to compute things. And you went to this very theoretical course in Yogyakarta, and you come back as a better human being, and now you have to say something. What is the Galois group? C what? Yeah, it depends what the name of your group of order 2 is locally. So you say Z mod 2Z of C2 or whatever. And that's an easy one. So you say, well, in this case the Galois extension is just, if you join a root, you get the well-known extension Qi over Q. And it comes with complex conjugation. If sigma x is x bar, then you see that this Galois group has order 2, and you're done. But if your grandmother was an engineer, or you ask the engineer right away, he may make your life a little bit more complicated. And say, well, quadratic is a bit easy, right? Can you do cubic examples? So you're given, say, x cubed plus x plus 1. And now you're unhappy there's an x. If it would have been x cubed plus 1, it's a bit like third root of unity, or maybe sixth root of unity. Yeah, that's something with q square root minus 3. That's exactly the same thing. But now there's an x. You say, oh, yeah, there were radical formulas, but he didn't treat them very well because Bas was in the audience. So then you need another way to still find the Galois group. And maybe your engineer asks, is this, by the way, an irreducible polynomial? Is it? Why is it irreducible? Let me say that for me, from now on, just to simplify life a little bit, I will take f equal to q. So, I may change my mind later, but for now it's q. So, why is x cubed plus x plus 1 an irreducible polynomial? You have to work on your role, right? You get home as the expert. So no long pauses, you say right away, of course this is irreducible, you see. Why? We'll send you to the next course. I mean, you really need to work on your performance as a mathematician. It's just to show, right? Most people cannot check you're a mathematician. So you just play it. There's two answers. Some people say, well, it has no roots. Since they know that roots of polynomial, monic polynomials, integral coefficients have to be integers. And they say, well, any root would divide 1 and plus and minus 1 do not work, so it's irreducible. There's also people who like primes. And they say, well, if you look at the polynomial mod 2, I can just check the zeros, 0 and 1, and they both are not zeros, so it's irreducible mod 2. So f is irreducible mod 2, which makes it irreducible also over q. Which means that if you adjoin a root, you get a cubic extension. And the problem with this whole splitting field is that you always have to adjoin all the roots. And the first step is completely explicit. Yeah, so you just take qx mod f if you want to form a splitting field. So to do this, for f equal q, you first form the field q alpha, which is qx mod f, where f is your irreducible polynomial. And then you know that it has 3 roots somewhere, say in q bar, alpha 1, alpha 2, alpha 3. So this is q alpha 1. And you have to enlarge it to form the full splitting field, alpha 1, alpha 2, alpha 3. That's really a slightly more complicated procedure, since you've seen that if you start with say a polynomial of degree 4, this one might have degree 8, or well, now it's cubic, so that was like a quartic example. Anyway, this degree is something which is not in general obvious from the polynomial. So this splitting field is something we don't want to work with too much, since in a way we don't even know what it is. And in particular, we, how should I say it, only want to use the field, which is not even a Galois field in principle, because it's not normal, it doesn't contain all the roots. The field with one root is typically good enough to determine what the Galois group is. And in this case, the easiest way to show that the Galois group, well, what can a Galois group of a cubic polynomial actually be? How many choices are there? Irreducible cubic. Just 2, right? It's either it's a subgroup of S3, and it needs to be transitively on the root, so it's either it's A3, the cyclic group of order 3. So in this case, because it's cubic, the Galois group of F is S3 or Z mod 3Z. If you want, you can call it A3 to make it look like a subgroup of S3, but it's anyway the cyclic group. So it works if you think that your neighbor will not go beyond degree 3, that you know a quick way to decide whether it's S3 or A3. Can we think of a way, in particular for this particular polynomial? How do you see whether the Galois group is S3 or A3? Discriminant, that looks like a calculation, right? Do we really need a discriminant?
I think the product of the squares of each.
Let me give you another example, which is an example that was already on the board also in the first week, I think. We spent some effort computing an irreducible polynomial that was also cubic and that looked like x squared, I think, minus 2x minus 1, which is also cubic. And the reason that we discovered this polynomial was that we were talking about Galois theory in Q zeta 7, which is a Galois extension with group Z mod 7 Z star, cyclic of order 6. And there was a cubic field that we called Q zeta 7 plus zeta 7 inverse. This is cubic and this is quadratic. And for the element alpha, which is zeta 7 plus its inverse, we computed the irreducible polynomial just by writing down the powers. Yeah, I remember writing down alpha cubed, subtracting 3 times alpha, and then staring at it and deciding that this was the polynomial. That was a while ago, right? And in this case, you know that the Galois group, this is Galois theory, this is cyclic of order 6. Here is a group minus 1 mod 7, cyclic of order 2, corresponding to the subfield. And if you take z mod 7 z star, and you mod out by this subgroup of order 2, C6 modulo C2 if you want, you get cyclic of order 3. So in this case, the Galois group of F is going to be A3. But typically, if someone gives you a polynomial without telling you that he computed that polynomial in a clever way to make it cyclic over Q, how do you discover that this is a cyclic polynomial and that that one is not? So someone mumbled something about a discriminant, and of course feel free to compute that discriminant of that cubic polynomial. That is some work. And you can of course also give it to Paris or Sage or something. But there's a much easier way. In this case, if you look at f modulo 3, how does it factor? How many roots does it have? It has been chosen to, obviously, if you plug in 1, you get 3, which is 0 mod 3. So it has a root, right? Actually, it does not have multiple roots, mod 3. And 3 is this is the only root. So f is linear times quadratic modulo 3 without any calculation. And my claim is that whenever a cubic polynomial factors modulo prime p, say it doesn't have multiple roots mod p, as linear times quadratic, then you know right away that the group is S3 and not A3. So my claim is actually that if you do this mod p for any prime p, it will never factor like a linear and a quadratic polynomial. Is that something we can prove? Is that obvious? Yeah, so you see I'm trying to push you to sort of understand that from the reduction of your polynomial mod p, how it factors, you can derive information on the Galois group. Well, why would that be? If you go mod p, right? This is in fact a polynomial which generates a cyclic cubic extension, so it's normal. It means that in this field Q alpha, if alpha 1 is a root of this polynomial, you know what the other roots are. Alpha 2 is zeta 7 square plus zeta 7 to the minus 2. That's because if you take z mod 7 z star modulo sines, you get a cyclic group of order 3, which is generated by 2. And if you apply that twice, you get the third root, which is zeta 7 to the 4 plus zeta 7 to the minus 4. And you see that in this case, once you have one root, you also have this root, because this is just the square of the previous one minus 2. And in the same way, well, here you think about what it is, something involving alpha as well, you can do the calculation. You see, once you have alpha, you have all the roots. And that is something you can also see mod p, if you go modulo primes. So I'm going to state a very nice theorem to work with this, and we're going to apply it. So yeah, so this argument proves that as soon as your polynomial has a root mod p, then it has all the roots, because if you take that root, you square it and subtract 2, you get another root. So either it has 3 roots or it has 0 roots. So that means that if you go for f mod p, it is the way it factors is either linear times linear times linear, or it's just irreducible of degree 3. So it's only 2 possibilities. And in this case, Well, you see it can be irreducible. It can then be linear times quadratic. Can it also be linear times linear times linear? Another interesting question. If you have a polynomial that's irreducible, is there always a prime with a property that it splits completely into linear factors? And of course, if you don't know, factoring mod p is a bit painful by hand, especially if you're lecturing and you don't have anything. But nowadays, online or on your computer, you have things like Sage and Paris and whatever. And even if you're lecturing, you may know someone who has it. And I happen to know René, who's sitting there. And he has Paris. So if I just ask him, is there a prime for which this has splits into linear factors, he can probably tell me.
There is.
And which is the smallest one, René? Oh, you didn't program that. Okay, so well, René, anyway, this always happens. You can compute it. So in fact, there's 3 times, so in the way this polynomial can factor mod p, I will always exclude the finitely many primes for which you get multiple roots. So that's in fact primes and discriminant if you want. I'm just assuming that primes I'm looking at never divide the discriminant of the polynomial. So it's always separable mod p. I throw away finitely many primes, I don't care about them. So here you have 3 possibilities. It can be irreducible, and you see writing things like linear times quadratic and linear, linear, linear. Let me just define for the polynomial of degree n the decomposition type, mod p, decomposition type. I just want to call this 1, 2, for instance. And linear, 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 that is just 1, 1, 1. And irreducible is just 3, right, for a cubic polynomial. So the decomposition type just means that you have d1, d2, up to dk, a tuple with the property that the sum of the integers is equal to the degree n, and they're all integers that are positive. So some people call it the partition. Yeah, so you can decompose your n as a sum of positive integers. There are going to be degrees of irreducible factors. And the question is, which decomposition types do you encounter? And what do they tell you about the Galois group of the polynomial? So for this polynomial, if you believe René, actually 47. Obviously, if you go mod 47, it has 3 roots. Please check. And if you believe, I believe René. If you don't believe him, you can look at it yourself. So, sorry? Well, you know, yeah. Tell me.
35, 34, 25.
What did you say? 47. So you see, all 3 possibilities do occur, just by numerically testing. So the decomposition types are 1, 1, 1, they're 1, 2, and they're 3. 3 types. In this case, there's only 2 types. Since I said if you have a root, mod p, then you have 3 roots mod p. So if there's a root, so you have only 2 types. And actually in this case, you also know how frequently they arise. Namely, you know it if you know a very well-known theorem. Namely, what does it mean that this alpha, this root exists mod p, so f has a root mod p. This f I mean, right? I'm on this board. Has a root mod p. That means exactly that if you look at zeta 7, you take any primitive 7th root of unity in characteristic p that generates some extension of fp. And the question is, if I take zeta 7 inverse, zeta 7 plus zeta 7 inverse, as you see, I'm assuming now that p is different from 7. That's exactly because my assumption. There may be finite many primes for which life is a little bit more difficult. You don't care. Question, does this element lie in fp? Well, how do you test whether something lies in fp? You just take its pth power, and if it's the thing itself, then you're in fp, right? Fixed by Frobenius. Bos Frobenius. First time. I will say it at least 10 more times, I promise. So, you see, that if you apply Frobenius, raised to the power p, what do you get? You get zeta 7 to the p plus zeta 7 to the minus p, because mod p raised to the pth power is just termwise. And when is this the same? Well, if p minus p is just 1 minus 1 mod p, mod 7. So you see that this happens if and only if p is congruent to plus or minus 1 mod 7. As I said, if I say if and only if, I may always disregard to find how many primes, in this case 7, for which things may be wrong. And then the question is, how many primes are there actually that are plus or minus 1 mod 7? Do we know that? Sorry? Well, the question how many is not, are there infinitely many? Are there infinitely many primes 1 mod 7? If you want to say how many, there is this notion of density. If you say, well, if you take the primes mod 7, except for the prime 7, which is special, there will be in this group of order 6, and they will hit all the residue classes equally often, right? Doesn't that make sense? If you in living number theory, people actually prove this. That's called equidistribution. Primes and arithmetic progressions, Dirichlet, 19th century. So I don't even try and prove it. This is, so this is exactly for 2 out of 6 residue classes. So this happens for 33%, or maybe 1/3, let's not take percentages, we don't do economy, for 1/3 of the primes. If I say 1/3 of the primes, I mean if you take all the primes up to a large bound, and you see how many are plus or minus 1 mod 7, that's a fraction. If the bound tends to infinity, that tends to 1/3. So that's the colloquial way of saying this. You can also wonder, so in this case, you see that linear, linear, linear happens 1 out of 3 times, irreducible 2 out of 3 times. So you will actually find both types pretty soon. What happens here? This one has not been made as being contained in the cyclotomic field. And actually, if you work over the rationals, it'll mean that if it's not in the cyclotomic field, it will not be in a Abelian extension. The Galois will not be Abelian. That's a well-known theorem that we also are not going to prove. We don't need it. And you can also wonder how frequently these things occur. And if you play a little bit with it, so if you use Paris, you can, for instance, count how many primes up to something far are actually of this nature. You can do, how many primes can you do just in a few seconds? 1,000,000. Primes up to 1,000,000. This is René, right? He does Paris and he says primes up to how often? So which fraction of the primes has the property that this polynomial splits completely mod p? So then you just type it in your Paris or in your Sage, whatever you want to use. Maybe even Maple can do it, but don't use Maple.
I give you the proportion.
Yes.
So it's 1 over the proportions, right? If you,
Yeah, sure. I want a fraction. So this is 1 out of 3. Actually, I want to know this number, right? This is...
it is 1 over 6.0234.
If you take all primes up to 1,000,000, then this fraction is 1 over what?
6.0234.
So it's going to be like 1 over 6, right? And what do we expect for the 2 other ones? That's something you didn't program, so I probably shouldn't ask, right? So the question is, what are these 2 fractions? How likely is it that this polynomial remains irreducible modulo your prime? And can we sort of relate that to the Galois group? And if you start playing with this, you're going to discover something. And since we don't have a lot of time, let me already skip a little bit to the conclusion. Since these decomposition types, they're related to the Galois group in the following way. Namely, this Galois group of F, it produced the roots, so it will be a subgroup of Sn. And on this board, my example is actually n equal 3, but it doesn't really matter. And elements in Sn, you can write them as product of disjoint cycles, right? So they have a cycle type. And what is the cycle type of a permutation? You just put the length of all the cycles, and you also put the 1 cycles, you get exactly the same kind of thing. So elements here in the Galois group, they have a cycle type. And a cycle type is also a set of integers, positive integers, that add up to the degree n. And you may wonder, well, this n was about the n roots, so the way you number them doesn't make a difference. Well, not for the cycle type. If you number them in a different way, it was the first lecture by Bas, he proved that if you take 1 up to n or 0 up to n minus 1, same group doesn't make a difference. Same thing here. Any way you number the root, you get something conjugate, and the cycle type is actually well defined. So every element in the Galois group has a cycle type. And my claim is that the decomposition types that you find by going mod p for f are reflected in the cycle types of elements of the Galois group. Let me phrase it a little bit as a theorem. It's going to be a vague theorem. So the claim is we take f in qx irreducible, just like in the two examples. And they claim that for every, so as always, I restrict to primes that do not divide the discriminant, which just means that I never look at factorizations having multiple factors. That excludes finitely many primes. So then the decomposition type is of that nature. For every decomposition type d1 up to dk of f modulo p, maybe I shouldn't phrase it like this. If f mod p has decomposition type this, then the Galois group of f contains an element sigma p of cycle type d1 up to dk. And this element, which I will vaguely define in a moment, this sigma p, is called the Frobenius of p. So for every prime you create an element in the Galois group called the Frobenius. And this Frobenius is only up to conjugation, as you see from all my identifications, so I only care about it up to conjugation in the Galois group, but it certainly has a cycle type by its action on the roots of f, and the claim is that for every decomposition type you find an element. In particular, for this polynomial, being irreducible mod 2, you see that the Galois group, so for this f, you see that sigma 2 is a 3 cycle. Because f mod 2 is irreducible, meaning that its decomposition type is just 3. So there's an element which has cycle type 3, it's a 3 cycle. And if you look at sigma 3, the Frobenius at 3, what can it be? We discovered that sigma 3 is a 1 cycle times a 2 cycle, which is just a 2 cycle. And if you take any subgroup of S3 containing a 2 cycle and a 3 cycle, the full S3. So just knowing that your f is irreducible mod 2 and has 1 root modulo 3 tells you what the Galois group is. So what is sigma 47? Three linear factors, right? 1, 1, 1, 3 1 cycles. So sigma 47 is in fact the identity. Well, these are small examples. Let me do a slightly bigger example. Okay, you remember this, right? This is the main statement. Just to every decomposition type, mod P, there's a corresponding Frobenius element having that cycle type. So let's go to a degree 4 polynomial. So if your neighboring engineer is ambitious, he will say, okay, these radical formulas in degree 4 are really terrible, so you don't want to know, want to sort of show that you know them. X to the 4, I think, plus x plus 1. That looks like a generalization of this one, right? You want to know the Galois group. And for degree 4, the group already gets order at most 24, right? And polynomials of degree 4 have quite a few decomposition types, just like there's quite a few cycle types inside S4. Do we notice inside S4? What are the cycle types? 1, 1, 1, 1, 1, 1, 2, 2, maybe 1, 3. I will probably forget one. 1, 3, 2, 1, 1. Oh, sorry, that was not wise. That's the same as that one. Sorry, 2, 2, 4. 5 types, good. Okay, so there's 5 possible decompositions of polynomials of degree 4 modulo P. And in this case, finding primes with the various decomposition types is a little bit more work, so now we really need René. So, René, what can you tell us about the factorization types? For instance, how often does it split completely mod P for the first whatever? Yeah, why not?
So then the proportions are for the 4, the type 4, the last one, it is 1 over 1.988. And then for the 1.3, it is 1 over 3.001. And then for the 2.2, it is 1 over 7.995. And for the 1.12, which is 1 over 4.002. And for that one, it is 1 over 24.2.
Okay. So if you want to answer the question 1 out of how many primes, it's irreducible. It's 1 over 1.988. If you would need to prove a theorem about it, what would you guess? Looks pretty much like 1 over 2, right? Yeah, so if you believe numerical data, sorry? Do you believe this?
No, that's not correct. It is 1 over 3.988.
Ha. Of course, you have to believe either René or Paris or both, right? So, such numbers mean that it should be a quarter. So, a quarter of the primes, you should be irreducible. And 1 out of 24 primes, it should split completely. And this is 1/4, 1/3, 1/8. Can we explain this? It's pretty irregular, right? There's 5 types of decomposition you can have, and they occur with completely different fractions, just by staring at numerical data. This is the way you discover theorems, right? What should be the underlying theorem? Can we sort of have an idea what these fractions come from? First of all, what do you think that the group is in this case? So what is the Galois group of F? You see that all these cycle types, they occur, right? So it must be the full S4. Yeah, it contains elements from every conjugacy class. And yeah, that means that it's going to be the full group. So the Galois group apparently is equal to S4. It's not necessary to compute all these fractions, just to do a few primes, have a few cycle types, and then conclude that these cycle types, just like here, if you have a 3 cycle and a 2 cycle, then you get S3. For S4, you also don't need much. So you take the first few primes, you get a few cycle types, and you conclude it's S4. So you never compute explicitly in any way this degree 24 field by generators over whatever. You just look at F mod P. You compute essentially its Frobenius as a group, as an element of the Galois group. And we still want to understand these fractions. For instance, why would this be 1 over 24? Why is the probability that a degree 4 polynomial with group S4 splits mod P with probability 1 over 24? What is the relation of 24 to the group S4? The group order, right? And as I said, what does it mean that it splits completely? It means that the Frobenius element, sigma p, is the identity element. So if you think of this Frobenius element in the Galois group as some sort of random element, yeah, if the group is a Z mod 7 Z star, it's about primes mod 7, and you say, well, that's a well-known theorem. It's just equidistribution, yeah, it's all 1 over 6, all the same fraction. Here life is a bit different. For the Frobenius to be the identity element in this group of order 24, yeah, it's the unique element you want, so it's 1 over 24. Why is this a quarter? So why does, for 1 out of every 4 primes, you get exactly 2 roots mod p and an irreducible quadratic? Corresponds to the 2 cycles, right? It means that sigma p is a 2 cycle. How many 2 cycles do you have in S4? 4 choose 2, right? Which is 6. 6 out of 24, that's a quarter. So you see there's just 6 2 cycles. So you view this as 6 over 24, and you say there's 6 2 cycles. 2 cycles. How many 3 cycles are there in S4? Well, if you believe this, it should be 1/3 of 24, 8. So even if you don't know what S4 was, but that's in fact an easy computation, there's 8 4 cycles. So it's 8 3 cycles. So this is 8 over 24. And that corresponds to the 3 cycles, the 8 3 cycles. 1 over 8, apparently 3. You know these are just the disjoint 2 cycles. There's 3 of them. With the unit element, they make this V4, this Klein 4 group inside S4, right? So you see that apparently the structure of sigma p, the element, yeah, inside this conjugacy class, obviously, it's assumed exactly as often as you expect it to happen. So this is called equidistribution. So sigma p is equidistributed over the Galois group of F. That's a bit of a vague statement, of course, but so it means that if you look at your Galois group as a permutation group on the roots and the associated cycle types, they're all assumed equally often. And sigma p is not a well-defined element, it's a conjugacy class, and the size of the class actually tells you how frequently the thing is assumed. So in particular, if you just count for how many primes the polynomial splits completely, which means that sigma p becomes the identity, that happens 1 out of n times with n the order of the Galois group. So a numerical way to find the order of the Galois group is that you just factor mod p for p up to something, and you see how frequently that happens. Do we have a nice example, René?
Yeah, you want x to the 4th minus something.
Let's take x to the 4 minus 2. That was where we computed the Galois group, right? Do we remember what the Galois group was? It was not S4, right? It was a dihedral group. Well, can you do it again at p to something?
Yeah.
So splitting completely 1, 1, 1, 1 for p up to 1,000,000.
Yeah.
Fraction 1 over.
Okay, so the cycle type 4, so the last one, is 1 over 4.000.
1 over 4.000. A quarter apparently.
Cycle type 1,3 doesn't occur. 0 times. And then the cycle type 1, 1. What is this one? Let me see. 1, 1, 2 is 3.990.
This is what? 1 over 3.99?
0,
Yeah.
And then the totally split is 1 over 8.035. And then the 2, 2.
Yeah.
2, 2 is 1 over 2.6667.
6667.
And then we should multiply it by 3, and then you have this. That's correct, I checked. 3, 6 is actually.
This is 1 over 2.66? Oh, amazing.
3 over 8 is also.
2 2/3, 8 over 3. Okay, so 1 over 8, 3 over 8, so maybe the 1 over was not the right thing to ask. 1 over 4 and 1 over 4, right? So you see that the Galois group has order 8. It's inside S4. That already, if you know about S4, that has to be a two-Silov subgroup, so this already shows that it has to be D4. And this is indeed exactly what happens for D4. You know what D4 is, right? That is the symmetries of the square. And that consists of is generated by rotation and various reflections. This one, that one, and that one. That's a mess. And it means you don't get all the permutations. So for instance, why is there no 3 cycle in this Galois group? Why is there no automorphism of the splitting field that fixes just one root? Looks a bit strange, right? But there's a good reason. Why is this group not equal to S4? You know, if you have one of these roots, like the 4th root of 2, and suppose you fix it, well, then there's another root, which is minus the 4th root of 2, which is also fixed. If you have a root, minus the thing is also a root, meaning that if you fix one root, you fix at least 2. So you cannot have a 3 cycle. So from the missing cycle types, you discover what the group is. And you get more information than you need, the 1 over here you get the group order, and D8 inside, so this is generated by whatever, a 4 cycle, 1, 2, 3, 4, and something that sends it to its inverse, whatever, 1, 4, 2, 3 or something. And if you just look at the cycle types, so the rotation rho and its inverse are the 4 cycles. 2 elements out of 8, that's a quarter. And the reflections, there's 2 kinds, namely they can either swap only 2 of the points, 2 of the roots, or they can actually do it in 2 pairs, exactly these 2 kinds. And there's 2 of them for each of them, I hope. No. Two, 2. Oh yeah, if you have a row squared, that's also a 2, 2. That's why. All right. So you see that if you know the groups a little bit, you look at these fractions, you get exactly what you need. This equidistribution has a name. It's the result that goes in the name of Chebotaryov, a Russian mathematician. Chebo. It's an extremely useful theorem. It's often used in number theory the way I'm talking about this, I'm not really mentioning exactly the relation with number. Most people actually do algebraic number theory if they discuss these theorems, but you can discover them all by yourself just looking at polynomials in Galois theory. Yeah, this is not immediately number theory. Of course, if you think about it, let me just conclude with an argument what this Frobenius is, just to make Bas happy. So how should you think of the Frobenius element? Sorry? Isn't it supposed 10 to 4? Oh, really? I thought it was up to 50, no? This schedule, they change it all the time. So I just have your... It's your crappy website. I looked at your website. Okay, guys, yeah, then Bas will be angry with me since you're going to miss the definition of Frobenius. Okay, if you want to know the definition, there is a very nice paper actually which I wrote long ago together with Hendrik Lenstra, which gives an easy introduction to the theory of density theorem and about the life of this Russian guy. It's fun to read if you don't like math, you want to learn about Russia, whatever. Okay, sorry for going over time.